Hi, welcome to this case study. Today we will be looking at Uyuni and in particular spacewalk reposync, which is an essential component, a command line tool actually running in each Uyuni server. And I will be explaining how I put together some patches that were landed to the Uyuni project via pull requests that make this tool run about 6 times faster than the version that we have right now. So I'm going to talk about 3 things today. First is the Uyuni community member point of view. What does it mean for you as a user? What does it change in daily use of Uyuni for you? And how can you make your next reposync faster? I will share some tips that are always useful in case you have this particular operation which is running too slow for you. The second thing that I'm talking about is the developer perspective. How can you improve the performance of your Python code, of your PostgreSQL code? Can you take some ideas out of this work to use in your next project? And thirdly, I will talk about the next steps. What can be done now as a continuation of this work? Where can we go from there? So, as I said, this project is basically the result of this project is 4 pull requests, which are named without a lot of creativity: reposync speed up part 1, 2, 3, and 4. But at the end of the day, what all of these do is just to improve the performance of a particular command, which is called spacewalk reposync. So if you are a long-time Uyuni user, you will certainly know this tool. Otherwise, suffice to say that this command will download RPM or Debian packages, and it will copy them to your Uyuni server. And in particular, after downloading, what it will do is to process the metadata that's inside of RPM or Debian packages. And it will insert it in the PostgreSQL database that's inside of your Uyuni server. So basically what spacewalk reposync really is on one hand a downloader, on the other hand a metadata ingestion mechanism of some sort. Now I mentioned that all of this work went into the direction of making it faster, and the natural question is, why is it slow? First of all, as I said, spacewalk reposync is a downloader. So if the download is slow for whatever reason, physical reason, pure data transmission reason, there's not much we can do about that. And the patches that I prepared, in fact, do not affect that part at all. But the package metadata mapping, so the work that spacewalk reposync has to do in order to extract data from RPM packages and insert them inside of the database, this is something that we can work on, and this is actually the main focus for my work that I'm presenting today. So as usual, when we are talking about a software product, we have 2 kinds of complication. We have essential complication and accidental complication. And what I mean with that is part of the fact that this tool is so slow is due to the fact that the problem that the tool is trying to solve is essentially complicated. And I will show you in a minute the detail for that. So this code is doing non-trivial work, and a part of that can't be eliminated completely. But part of that is accidental complication. So it happens that because of historical reasons, we have some code paths that are particularly inefficient, and that can be optimized away. And this is my focus here. So why is it essentially complicated to get metadata out of, for example, RPM files and put it in the database? You can have an idea by looking at what is the kind of data that we're talking about. So, for example, let's take the RPM command, what you can do is use the query flag and, for example, the info flag. And if you do that with the name of a package that you currently have installed, you will get some information that's contained inside of the package itself. So there's the package name, the package version, the release, the architecture, and a lot of other pieces of data. So you can easily imagine that this is easily copied inside of a database. It becomes more complicated when we look at some other pieces of information which is also contained in the package files. For example, the list of files which is inside of the package. Now, in this particular case, if we count them, it's not that many. It's just 150 files. But there might be other packages which contain a lot of files. So this becomes a bigger information set. But more importantly, you might have several files which share some of the files, provide the same file. And then the problem will be to deduplicate those files across packages. So we only want to store this particular string with this particular path once. And we want all packages that contain this particular file to share the same string. So we want to deduplicate the list of files across many packages, across many repos, across many distributions in the worst case. It gets even worse if you look at some other metadata. For example, the provide symbols. Now, this is a list of symbols, optionally with a version, that is provided by this package, and other packages might require. Now, in the case of Vim, it's just a very few of them. But if we take, for example, the kernel, the list becomes very big. In case you can see that, we're talking about tens of thousands of provided symbols. And if you sum the provided symbols and the required symbols and all of their versions and the files across all packages of a certain repo, including different versions of the same package, you get very quickly to millions of rows that have to be deduplicated. So this is quite an amount of data. But what is more important is what we want to do with this data. So how do we need to transform it? Now, I will show you something which is a little bit technical here, but still gives you an idea. So this is, sorry, I have to open it with another application to show it better. This here is a diagram of the database tables, of the most of the database tables that are involved in Spacewalk RepoSync. And here we can see, for example, the RHN package table, which is the main one. It contains an ID, name, version, architecture, and other metadata. And of course, there's one of those. There is one of those tables in your server, and each row will correspond to a package. But now there are several other tables, if we zoom out a little bit, which contains data which are related to each package. For example, each package has a set of repo data. It has a set of changelog entries. It might have an architecture, it might have a source RPM and so on. And in particular, there's yet another big set of interesting properties here, which are collectively called capabilities. What is a capability? Might be something that the package conflicts with, something that the package requires, something that the package supplements, recommends, provides, obsoletes, suggests, etc., etc. And in particular, there is the file. Each file is also a capability, and each file also has a checksum. Now, the crazy thing is not just the complexity of this drawing here, but the fact that each one of those tables are, technically speaking, normalized, and it means that the data inside has to be deduplicated. So we want to have one row with a file for all packages, across all packages of any channels, any distro. One row for each capability, one row for each checksum. So we start from a set of data which is highly denormalized, and we want to come up with a set of data which is highly normalized. And this is essential complication. We can't get rid of that. Now the question is how to do this job in a way that is most efficient, and what can be improved from the current situation. Okay, so I talked about what spacewalk reposync is, why we are doing this work here. Who is most interested in the output of this work? Now, as I said, spacewalk reposync is triggered nightly for all users, but in most cases it's also quite fast because it will only transfer the delta, so the difference between the current version of the repo and the version that was last synced. So by default it runs nightly, and every day some repos might change and some packages might change, but usually the number of packages that change daily is not that big. So normally spacewalk reposync finishes in a pretty fast way. There is one exception, and it is the first time that you added some new repo to your Uyuni server, and especially the first time you set up the Uyuni server in the first place, and you have to reposync a lot of different repos. And if you need to do that, then you need to wait for hours, and that's the use case that we are trying to optimize here. So the general community, of course, will get some benefits out of this work, although they might not really notice the difference unless they're really reposyncing a repo for the first time. But it is very important for people that do Uyuni demos. For those guys, it is super important that this tool runs fast, because it's on their critical path, and they will need to spend hours every time they prepare a Uyuni demo. And this is also true for SUSE Manager, which is the downstream for Uyuni. And the third category of users who are very interested in this kind of work is my QA colleagues, who need to set up Uyuni servers all the time to run tests and make sure that the product has no bugs. So this will definitely shave off some hours from their workflows. Okay, so when it comes to results, as I said, there's no change in the downloading part. Downloading will take exactly the same time. The computation that needs to happen after downloading will be about 6 times faster, even more if you have more CPUs, because part of the changes that I did are about the fact that the computation is now at least partially concurrent. So if you add CPUs, the tool will run faster. And also this 6 times factor that I've been talking about is pretty robustly transferable to many kinds of repos. So I've tried it with a very lot of different repos, and it seems like the factor is about the same for small repos or big repos or whatnot. So this will be the big change. One trade-off is that reposync will likely consume more memory than it used to consume before. Some gigabytes, usually. I have seen 6 in the tests that involve the biggest channels. So keep in mind that this could consume some extra memory. So it's definitely recommended to have 16 gigabytes of RAM for your Uyuni server. So this is one downside. You can expect these changes to be in the next Uyuni version or the next major System Manager release 4.1, which is slated for release to this summer, late summer. I also have a few tips for you when it comes to how to speed up my reposync. Those tips are also useful today without the patches that I'll be explaining. First of all, if possible, it would be good to have some kind of repository mirroring. So instead of downloading all the packages from SCC or a remote server, you could have a Minima server or an RMT server. I have the link here. I also have some notes that I will share at the end of the video, so you don't really have to remember all of the URLs that I'll be typing and visiting during the video. So there are those tools. Minima is one, RMT is another one, that allow you to pre-download all the packages on your local machine or a machine in your network, and then you can reposync those this content to your Uyuni server. So if you set up Uyuni often, for example, if you are a developer or a QA engineer, this is definitely recommended. Also good if you do demos. The second tip is whenever possible, use an SSD because an SSD, this is also pretty IO intensive, so an SSD helps. 16 gigabytes of RAM, as I said before. Some CPUs, the more the better. 4, 6 are good starting points. If all you're doing is testing, you might want to disable Spectre meltdown mitigations for Intel CPUs, in case you have an Intel CPU. There is this nice website which is called makelinuxfastagain.com that will give you a nice one-liner for your kernel line. This will get you another about 5% speed up for free. Of course, this is totally unsafe if you use your machine in a production environment, but it's okay if all you're doing is QA, for example. Another important thing that I discovered at my own expense is you really want to have your laptop connected to power in case you run this on the laptop. Why? Because running on battery will activate some BIOS and kernel procedures to save the battery, and this will mean that your CPU will run slower. So in my tests, this impacted quite a lot, about a factor of 2. So it was twice slower if I disconnected my laptop from power. So it's definitely recommended to keep your laptop connected if this is your setup. Okay, that's it for the community, Uyuni community member point of view. And from now on, I'm going to concentrate on the technical side and going much deeper into the developer point of view. Once again, I have 3 points in the developer agenda. The first is some tips for doing correct and quick and accurate testing in general of any kind of software. So there are things that you have to keep in mind, and there are some practical measures that you can take. And once again, I've discovered the hard way myself. So keep those in mind next time you want to do some performance work on a piece of code. The second thing that I'm going to talk about is tools. I've come to know a few specific tools for Python and Postgres performance work in particular. So I want to share the experience of the specific tools and some tips on how to use them in your next project. And the third thing that I'm going to do is to have an overview of the exact changes So what were in detail the improvements and how those can be also transferred to other areas, other code bases, other cases, and so on. So let's start with tips for accurate and correct and quick testing. One thing that I've learned is that CPU throttling is a thing. So there is this nice GNOME application which is called CPU Frac. You can find it on the GNOME extensions website, and this will expose a number of settings on how your CPU speeds up or slows down depending on various configurations. So for example, you might have different settings in case your laptop is connected to the battery or not. And what you want to do is something like this. So to basically peg the CPU speed at a certain percentage so that you can run several tests and make sure that the differences that you see between one test and another are actually due to the changes that you've done in the code, and not to the fact that the governor in a particular situation decided to use a higher frequency or use more CPUs or take some cores offline because of thermal capacity reasons, because of power capacity reasons, because of concurrent programs, and you name it. So this was something that helped me normalize the numbers quite a bit. Not only this is managed by the operating system, but it's also managed by the BIOS itself. So when I turned on the BIOS in my computer, I could see something like this. And this completely overrode any setting that I had here in CPU Frac. So it's really important that you check both. Otherwise, you might run into the situation that the CPU frequency should be pegged at a certain number, but actually it fluctuates. Why? Because it's the BIOS changing it. So once again, choose your parameters wisely so that you don't get surprises down the road. The other important thing when testing in general is having repeatable conditions. And there's many ways you can accomplish that. You can use Docker containers, you can use VMs, you can use any other set of tools. But the important thing is that every time you run a test, you are sure that you're running exactly the same, in the exactly same condition every time. So I went for a kind of easy way, nothing very fancy. Here I just created VMs with KVM, and one of the things that you can do with KVM and libvirt is to use snapshots. So I just created one snapshot which is called before RippleSync, and every time I do a test I revert to this snapshot. This is a very, very easy way to do it and to make sure that you're always looking at the same environment whenever you're testing something. There is one important thing to keep in mind though, and it's the fact that when you revert the snapshot to a given, you revert the state of virtual machine to a given snapshot, you might lose synchronization of the current time. So I can show it to you very easily. So here at this point, if I run the date command, the clock is already off. It's 4 a.m. Now what I do is I start the snapshot again. So the state of the virtual machine is now being brought back to the state where I took this snapshot. The SSH connection is obviously broke down. But if I log in again, and then I run the date command again, now it's 9 p.m. And this could confuse your measurement tools, and in particular the profiler tools that I will talk about in a minute. So what you want to do is to make sure that as soon as you've started the virtual machine from a certain snapshot, You also run an NTP updates to make sure that the date and time are correct. And this is before running any test, any code. To make my life easier, I've created a shell script which does many things, which I will explain in a while. But what it does mainly is to revert a sort of snapshot. And after that, it will run those two commands. And those two commands, they will start the cronny daemon and force it to make an NTP synchronization, really solve this problem. You might be familiar with the NTP date command. Now NTP date is not used anymore since we have systemd, but this is basically the equivalent. And yeah, this makes sure that whatever you run after that, in particular profilers, don't get confused by the fact that you've just restored a VM snapshot. Another thing that you might want to keep handy is some snippet, and this was a snippet in my case, to do some quick testing. So what you will be doing is to run a test. Okay, it concludes in 1 minute. Then I change something in the source code, and then I run another test again. And chances are your changes completely broke the program. So it's not always that easy to make sure that your modification didn't actually completely broke what you were working on, instead of just improving the performance. So what I found very useful is to have a one-liner or a very short snippet that I could copy and paste, just to make sure as a smoke test that I didn't break anything in a major way, and then run the proper test, which could last some minutes or even some hours to assess performance. So I think this is handy in this particular case, but it's also something you want to keep in mind in general. Another thing that I found pretty interesting was to wrap the script that would run the test in a very simple for loop like this, that would loop over several commits. So this command here, what it will do is to find all the commit IDs for a certain set of commits. Yeah, unfortunately I took the wrong one here, but this is the result. It's just a set of IDs. And then I take this list of commits and I do a for loop. Why? Because this is handy to test the incremental changes of several commits, to make sure that if your commit is just a refactoring, it will have an impact of 0 or almost 0. And if your commit is supposed to improve things, it actually improves things in autonomy without taking into account all other commits that might be in your branch. So this is how I came up with some fancy tables that are in the PR description, where I have the list of commits and the speed up on a commit by commit basis. What I do is looping here, and then I save the end results. So I grab the total time from the log and I save it to some file, and then I combine all those files together in a simple LibreOffice worksheet, so that I can compute those numbers. I know it's a very manual process. It's nothing very fancy, but it really saves you a lot of time, especially if you want to go to bed while launching a very long set of tests on all your commits, and then next morning you can look at them with a fresh mind and say, okay, what worked and what didn't. All right. A couple of extra very generic notes to keep in mind. Here what I did was to test, to run all the tests on the same machine that I was using to develop. This is, of course, not entirely optimal. Ideally, one has a test machine which is completely separated hardware in order to be absolutely certain that processes running on the developer machine don't go corrupting the measurements that we do on the machine under observation. In this particular case, the noise level from my development machine was absolutely tolerable, so it can be done in simple cases. But of course, if you are trying to be very precise, keep in mind that you might want to have a completely separate server to keep under test. And the last recommendation, of course, is to always measure. So never trust gut feelings, not too much at least, and make sure of what you see, because optimization is kind of an art that can be very confusing sometimes and can lead to very counterintuitive results. So my suggestion is always measure. Which brings me to the next topic, which is a topic of tools, and in particular the topic of profilers. And I want to talk to you about two profilers that I have used in this project. One is called PySpy and one is called Austin. So both are profilers for Python. PySpy is very easy to install. All you have to have is pip. In case you don't have pip installed, you can use the get pip script, and then you run it on Python, then you install PySpy. It's very easy even on systems that don't have pip at all. So actually, it's not written in Python, despite the fact it's distributed in pip. This is actually a Rust project. The fact that they publish it in pip is just for convenience for Python developers. And what it allows you to do is several things, but the most important is it allows you to record a trace of a certain program, or a certain PID in case the program is already running at that point. And out of this, you get a profile file, which could be an SVG like this one. We will go through that to a moment. It will tell you what the program was doing while it was running. In my particular case, I have this command line here. I can just copy and paste it to explain it in an easier way. What one does is to run PySpy record. You can choose optionally to also trace native code called by Python code. You specify an output file with a format, and I will go through that in a minute. And you can also get the function name optionally, and then you run your program. So it might be Python 3 and whatever else, or a name of a Python tool like spacewalk, repo sync. Interestingly, in this case, it's not installed. I think it's in this directory. No, it's not here. Okay, never mind. Anyway, the end result is a file that can come in two formats. In the first case, you have what is called a flame graph, which looks like this. It's called a flame graph because it somehow resembles a flame. Here you have a bar representing every function, and bars underneath it that represents other functions that are called by that function. So in this case, for example, we have a method name is called fix, coming from this particular file, package import.py, and this calls fix again, and it calls process capabilities, which calls execute values, execute wrapper, and so on. And the important thing is that the length of the bar is proportional to the time that the particular function took to run. So if you look at it, even at a very high level, you can see there's basically two big functions. One actually boils down to downloading the RPMs, and the other one boils down to the processing in this case. You can also, you have a very nice search button, and you can search for a given string, and it will highlight all of the bars that have that string in their name. So this is a cool, very cool tool, because it allows you to concentrate on the most important parts of the code base, and you can also see sometimes if parts of the code base are slower than you would expect them to be. So you can dig deeper and find out if you can rearrange them somehow. Another interesting thing is that it will also trace native code. So here, for example, we have the doPerform function in the grabber.py file in the standard library of Python. And then you see the flame goes down inside of native code. This was particularly important for this effort because a lot of the code was actually in PostgreSQL. It was in C libraries that we use in order to extract metadata from RPMs. It was in libcurl, so I had a much more complete picture of what was going on via tracing of native functions. This is not the only format that PySpy supports. There is also another format, which is a JSON file, which can be put inside of a web application which is called Speedscope. And I have an example here that you can just go to speedscope.app and you get this one-page app, which runs completely offline, by the way. You feed it with the JSON file, and then you get a very nice or messy, depending from the point of view, view of the flame graph. It's another way of seeing the flame graph, and in a way it's much more fully featured. So first of all, you can see up here we have one of 6 counter, and this is because this Speedscope visualization will divide flame graphs by their process. So in this case, we are looking at 6 different threads or processes. In this case, it's threads. And you can see what each individual thread or process does. Second, you have some kind of a viewfinder here on the top. And you can decide to select only a part of what you want to see. So here what I'm doing is just to see a particular interval and moving it around. And if I do that, I can see more in detail what's going on here. You can also see that this view will show all of the stacks in their time order. So this is exactly what happened. So here we had one call to fetch URL, then another one, then another one, then another one, then another one. Which is interesting to see what the program was doing at any given point in time. It's also pretty confusing, especially if what you really want to learn is what are the most time consuming functions. So if you want that, you can click on this button up here, left heavy, and what you get instead is one only bar for each function, which was called in the same way, basically. So you can see that, for example, in this case, you have one run function, which does everything, basically. and 2 different calls to fetch URL, which in turn boil down to different stack traces. So this is also cool. You can see here we have 6 threads. 5 of them look very similar because they are download threads, and what they do is just downloading RPMs in this case. And there is one which is different from all the others, which is this one here, which is about the processing. So you can see, for example, that process object collection is pretty heavy here, and also process capabilities here, process changelog. We will see those names again. But yeah, this was my main workhorse to find out where the weak spots were after a patch, finding out if that particular block was reduced in size and so on. There is one final thing that I want to show you about speed scope, and there is the sandwich view. The sandwich view is just a plain list, which allows you to see what were the functions that consume the most time or the most self-time. Self-time is the time passed in the function itself without considering the time spent in other functions which were called by that function. Well, the total is the total time. And if you click on one of them, for example, execute wrapper, you get all the callers and all the callees of this particular function, which is also sometimes useful. So yeah, with PySpy, you have an easier output. You have a more complicated kind of output if you want to dig deeper. It also does other interesting things. It has a top mode, which will show you what a certain program is doing at this point in time. It has a dump mode, which will just create a thread dump statically. It can be useful for debugging. So all in all, it's a pretty nice tool to know. At some point, I was also getting some strange results. I was not really sure about what I was seeing. So I also tried another such profiler, and that profiler is called Austin. This is a C project, and yeah, so it's a little bit more complicated to install because we don't have a package yet, but still I have instructions here in the notes that you can use. It's just a matter of basically configure, make, and make. Install is not anything super special. What is different in Austin? Of course, it has a slightly different command line, but it's not that different. The main difference is that it will output its own format, which then you have to transform in order to get either a flame graph or a speed scope file. Here I've created both, just for you to see. The flame graph is reversed, so we have the main function at the bottom instead of the top, but it's not very important. What is more important is that Austin will also tell you about particular code lines. So in this case, for example, we have the init method, and in particular, most of the time is spent in this line 118. This proved to be useful in some cases where I had, for example, a very long method or function, and I wanted to break it down to know what were the slow parts of the code. So this is also pretty nice. What Austin does not do is to go down into the native code. So it's Python only, and this kind of limited its usefulness sometimes. You can also look at a speed scope from Austin that I have here. Of course, the overall look and feel is not really different. No, I don't even have it here. So the look and feel is exactly the same, but the numbers will be a little bit different because they're broken down by code line instead of function. One interesting thing when looking at profilers is to have an idea about how much do they impact your code. Because of course running a profiler means that you have some extra code running on your machine that that profiles the code that you're studying, and that will of course cause some extra load. And the question is how big that load is, and does it skew my measurement, and how much does it skew them. And here I did a comparison between PySpy and Austin, and here you have some results. So here we have several commit IDs and those are the commit messages at that point in time when I did this, and those are the runtimes. So for example, 4 minutes 7 seconds was the best, and I was starting from the master version, which took 10 minutes, and this is the time in seconds. Now, how does this time in seconds change if I run the exact same tests under PySpy? It is slowed down, of course, and on average it's slowed down by 13%. So it's not a huge blow, but it's not zero either. So you have to keep in mind that running a profiler will slow down things a little bit. And what is the deviation? So how big is the slowdown in this particular test compared to the average? And this is important because if the deviation is more or less always the same, I know that the profiler has slowed down my code, but it did so in a uniform way. So I expect less surprises when comparing results. But chances are my profiler skewed my results in a very specific way. So there are some code paths that are very affected by the presence of the profiler, and others that did not really take any slowdown. And here you can see the numbers for Austin. So overall, I would say, yeah, Austin is much more lightweight than PySpy, at least for my use case at this point in time. So it's generally something to be recommended if you are studying a case live, for example. You don't want to have a very big hit on your code base on the runtime. But it also has a little bit higher average deviation. So this means that results tended to be a little bit more uniform with PySpy. So again, pros and cons. There's no definitive answer on what is the best profiler for Python at the moment. I suggest that you take a look at both depending on your use case. So we've talked about Python profilers, and we've talked about their differences. Now I would like to talk about some facilities that are about Postgres, which is the other part that I spent quite a lot of time studying. And turns out that Postgres has a number of interesting tuning knobs that you can use, and they're useful for studying performance. Now I have a short list here. The first one is called log min duration statement. So if you add this line to your Postgres configuration file, Postgres will save in logs any query that takes more than 100 milliseconds in this case. You can also turn it to 0, and that will just log all the queries, all the statements. This is useful because sometimes it's not clear from the profiler that you have a certain query that is particularly slow. Usually you can point it out, but sometimes this is not so easy to see, especially if you have a query which is repeated many times. It's not that long. It is significantly long, but not that much that you can see it clearly in the flame graph. You have it all over the place. So this is useful because then you can look at logs and find out, hey, this query is being called a lot of times and it takes a little bit. So it's cool to take a second look at it, see if I can optimize some index or change the query a little bit to make it faster. The second interesting thing is automatically explaining long queries. So if you've done any amount of Postgres optimization, you know that once you've located a query which is slow, the next thing that you want to take a look at is the explanation that the database can give you, because this tells you how the database planned and actually executed the query in low-level terms. And this can show you where the bottleneck is in an individual query. Now, the problem is that when you're developing and you have logging of slow statements on, you have to, every time you run your program, you have to collect the logs, extract the query. Oh, this one is slow. Let me run it again with the explain clause so that I get the explanation, and then I study it, and then I have to repeat it all from the beginning. If you have auto explain on, and you can also decide minimum duration, then you get automatically all the explain plans in your logs, so you don't have to copy and paste them every time. And then the next problem you will have is, how do I make sense of it? Now I have an explanation of how the database wanted to perform this query, but why is it actually slow? And this is a huge topic, and I'm just gonna touch it very briefly here. Basically, let me show you one such plan. It's not very easy to see what the problem is. So in this particular case, I was looking at this big query, and the result was this query plan. So yeah, I mean, it's possible, but not so easy to figure out what this means. We are lucky though that there is this tool, which is currently hosted by dalibo.com. The tool is called PEV2, and it allows you to import the query plan in this format, which is not that easy to read, and put it down in a nicer form, which is easier to comprehend. So in this particular case, I was looking at the same query under two different conditions that I have here. In one case, the execution time was 200 milliseconds, which was okay for the particular use case that I was looking at. And in this case, it took 13 seconds. So hugely inefficient, and I was not sure about the reason. And here you can see the single operations that the database was performing in order to implement my query. And you can see here there's a percentage of the time each operator took. So in this particular case, I could see that there was a slow sort that was taking about half of those 13 seconds. And the other slow operation was a CTE scan, which basically means the execution of this inserted capability subplan, which is represented here in this box. And if I look at it, those 6 seconds were basically spent in another CTE scan, which was also 6 seconds long. And if I look at it, what it does is again a sort. So the overall query was all fast, apart from 2 sort operations on the same table and the same column on the same table. Result, if I just had to add another index on this particular field here, and the query was sped up very significantly. Now this is relatively easy to see once this is finished and we have an explanation. It was not that easy to see when I was studying those plans. And here is another, I would say, superpower of anyone doing open source. And it's the fact that you can ask the authors. So in this particular case, I didn't know what the planner was doing. I couldn't make sense of it. So what I did was to reach out in the PostgreSQL mailing list and just ask a question. And I included as many details as possible to tell the Postgres authors what I was seeing and why. And I actually got several responses pretty quickly from people that had a lot of insight into Postgres internals, and that could explain why the plan was so slow. And I was particularly happy to see among the other responses, as soon as I can get it, a message from this guy here. This sir is called Tom Lane, and he's basically a legend in the PostgreSQL world, nothing less than a legend. He knows all of the PostgreSQL internals and design ideas very thoroughly. And I was really amazed to get an answer from such an important technical person in a matter of hours. That was really great. And of course, his explanation was also great. And I suggest you to have a look because it was a very interesting case as well. So I've talked about some PostgreSQL options. I've talked about this online tool here, which is called PEV, to run, explain, analyze. And I've talked about how to reach out to the communities for upstream projects and how that can be useful to understand systems we're working at better in the open source world. And that concludes my second developer-oriented part about tools. Now what I want to do is to have a look at the specific improvements that were included in those pull requests. And I will do that by just looking at the commits. Some of them were really easy, pretty obvious. For example, this one, we had some code that was computing checksums over files, and we just had the buffer, which was tiny, and just increasing the buffer allowed for a good speed increase. So this is somewhat typical memory versus speed trade-off that you can have. This was perhaps the easiest case. Another pretty typical case is to do more between two commits. So here we're doing something very database intensive. We're doing massive insertion, basically. And every now and then we commit to the database. And every time we do, all the buffers are flushed to disk. And this is a blocking operation and an operation that takes some time to complete. So here in this case, we had a parameter that set a default on the number of packages that had to be imported before we commit. And just changing this parameter did a noticeable difference. So whenever you're doing mass insertions, don't commit at every insert, commit a certain appropriate number of inserts, and if you are into tuning, try to see if it makes sense to increase this buffer. Another thing which is very typical for SQL systems is that in SQL you always work at batches of data. Usually getting one single piece of data, one single row, or one single value is the exception. And here we had such a case, and we were getting sequence numbers to insert new rows. We used to get them one by one. We just had a for loop. You can see it here. For entry in entry list, we would take the sequence column. Doing the same in a batch for many entries in just one query did a big difference. And this is something, this is kind of a pattern. Whenever you're working with SQL, try to always select multiple entities, insert multiple entities, delete multiple entities in one shot, because this usually yields big gains, and it's a good thing to keep in mind in general. This was a strange one. We used to have a class which extended userDict. In Python, userDict is a wrapper around a normal dictionary. This was a class that was used in earlier versions of Python. If you wanted to have your special dictionary, perhaps with a couple of extra methods, you could extend userDict and then use it as a normal dictionary from the point of view of the syntax. And what this does is to basically wrap a normal dictionary. Now, wrapping an object inside of another object and calling a method from another method is usually something which is relatively cheap. You don't really have to think, oh, I'm adding too many layers of indirection. But in some cases, if you are doing millions and millions of calls, this starts to have a price. And in this particular case, just extending the dictionary directly instead of userDict, which would in turn extend dict, made a quite interesting difference. So this is probably something not that familiar for Java people who are really used to a lot of indirection, also because the Java virtual machine makes it very efficient. In C Python, this starts to cost a bit. So if you really have a hot path where a lot of the same method is called a lot of times, you might want to reduce indirection a little bit. This might make a difference. So this was basically what was done for the part one of the repurposing speed up pull request. I will skip directly to part three. Here, completely different context. Here we are looking at the library that we use to access PostgreSQL. This library is called PsychoPG, and this is the equivalent of a JDBC implementation in Java for Java programmers. PsychoPG gives us a lot of different methods to interact with Postgres data, cursors in particular. And there is a particular method which is called execute many that you can use to execute a query against a variable, a list of objects. And unfortunately, this method is particularly slow. And in fact, the library warns you the current implementation is not faster than just executing the same query in the loop. And this is what you don't want to do in SQL. It's the same concept that I've mentioned a while before. You want to work in batches. You don't want to loop over something that just works on a single row. Fortunately, PsychoPG has added a few extra methods, which are called fast execution helpers, that avoid this problem and are actually much faster. One is called execute batch, and the other one is called execute values. So in the third pull request, what I did was to basically replace our use of execute many and similar functions with the new fast execution helpers. And this, without a lot of surprise, helped a lot in performance. It also allowed to do some other more interesting, from my point of view, optimizations on top of the new execute values methods. And here I want to talk about a very specific case, which is how we insert package capabilities. So, as I said before, capabilities are a table that has really a lot of rows, because some packages like a kernel can have tens of thousands of them, and each file in any package is a capability, by the way. So this table is particularly big and needs to be treated with a lot of care when we insert data in there. And in fact, back in the spacewalk days, they did use some special mechanism to insert there. Here we are looking at spacewalk code, and we are looking at Oracle store procedure that was used and is still used in spacewalk today to insert a capability. Why Oracle? Because in the beginning there was Oracle. What this function does is to try to select the capability given its name and version. If it is not found, it will call another function, another store procedure, which will insert it and then select it and return it. Basically, this lookup function ensures that the given capability exists. It will either return the ID if it exists already, or it will insert that capability and then return the ID anyway. If we look at the insert package capability store procedure, there's not a lot to see here. What it does between begin and end here is to insert the capability and commit. And this is the little bit strange thing about this function. And the strange things come from this pragma instruction here, autonomous transaction. What are autonomous transactions in Oracle? Turns out that in Oracle, what you can do is to have nested transactions. You can have a transaction, and inside of it, a nested transaction which is autonomous, and that means the inner transaction can commit or roll back without any effect on the outer transaction. Why did they use this mechanism? Because what they wanted to have is a mechanism to insert the capability regardless of the commit or rollback of the outer transaction. They basically wanted this insertion to work in any case. They wanted this to be foolproof. No matter what the outer code is doing, we want to be absolutely sure that the capability gets in. And that's why they use the autonomous transaction. And the basic reason why they wanted the autonomous transaction is to make sure that this insert will not fail in a breaking way if this table already has the line, the row that we're trying to insert. Basically, they wanted to guard against the case where two different threads or processes were trying to insert the same capability at the same time. Because if that happens, one of the two will break a constraint. And they wanted this error not to happen. So what they did was to use autonomous transactions here and to catch the exception in case it broke some index, it broke some constraint, so that they were absolutely sure that the capability would have been inserted in any case. This is all nice and working and fine and also performing well, I believe. I never tested it. If you have autonomous transactions, so if you are on Oracle. And unfortunately, Postgres does not have autonomous transactions. So they were facing this new problem. How do we make sure we can insert the same capability from two different processes and not having them break even in absence of autonomous transactions? What they did was to use, from my perspective, abuse a completely different mechanism that exists for a completely different reason, which is called db-link. The db-link is a PostgreSQL ability to connect to another PostgreSQL and run queries on a different PostgreSQL server. So from stored procedures in one server, you can execute arbitrary queries on a different server by opening a connection and acting as if you were really any kind of different program. So basically the second server would not know that it is being called by the first server. To it would be just another client program. What has this to do with autonomous transactions? Well, what you can do inside of a store procedure is to open a DB link to the same database itself and open a transaction there and commit it there and get an effect which is similar to having an autonomous transaction, because the link itself would act as an insulation layer, basically. So this is how it worked and still works in Spacewalk. So here we are again in Spacewalk code. This is the same store procedure, and this is what they do if the capability is not found. They will execute the insert via the DB link on the same database. And then again, in case there is a violation of some constraint, they will just select and basically forget that the insertion was not successful. Now, doing this will not work for Spacewalk RepoSync. Why? Because opening a database connection costs some time. And here we're talking about a function which can be called millions of times. So this doesn't scale. So they had to find out a different way of doing the same thing. And what they did was to resolve the problem at the Python level and not in the store procedures. And here's what they did. In the process capabilities method, they would open a secondary connection, but only once at the beginning of the execution of the whole Spacewalk RepoSync program. And then when their processing capabilities just running the query on the already open connection, so that they could share the connection between all of the calls to process capability. And in fact, what they do is they call a slightly different store procedure, which is called in the same name but underscore fast. And underscore fast means don't open a secondary connection because I am doing that for you. But still, this is low. Why? Because we are doing that for every pair of name and version. So for every capability, we are not working in batches. We are calling a select in a loop for every capability. And by the way, having a secondary connection, it means you have to commit every time you have a new capability. And capabilities might be very many. So this is not ideal. Moreover, they had to add another layer of locks, explicit locks, because in other cases this failed. So it was kind of a clunky mechanism that is basically there because it was not possible to restructure the whole code base based on the fact that Oracle had a certain feature, but Postgres didn't really have it. So it was kind of a hack, and in fact it was pretty well documented, but it was also understandable why they did it this way. Here's a new version that comes in the pull request. It uses a simple, at least a plain SQL query. It doesn't use a secondary connection anymore. It doesn't do tricks with locking anymore. What it is an insert which is fed from a select. And it has a particular clause here, which is called on conflict do nothing. This is only present in the latest PostgreSQL versions. And this is basically what we wanted to do all along. Make sure that the insert will not fail in case it breaks a constraint. So basically what I'm saying is that by using the latest and greatest Postgres, you get a capability that can be used instead of all the other mechanisms that I've been presenting so far. You might also notice a few things that are unusual about this query. One is this with statement. With can be used to define a table that is only it only leaves until the end of the query. It's as if I created a view called missing in this case, or wanted in this case, and immediately destroyed it after this query is finished. So it's kind of a temporary view, nothing really fancy. And here I'm using two. So first of all, I create a view on all the values, and those values are passed by Python. They're a set of couples name and version. So here I'm working batches. Then I create a view missing, which contains all of the capabilities that are not already in the table. So here where I join on the table with a left join, and then I check if the ID is null. That means find out if it's not there already. And if it's not there already, I already select the new ID. And then I insert into the table all of the missing rows. In case there's a conflict, do nothing. So with this query, which I admit it's a little bit verbose, it's not immediately easy to see, but it's pretty clean from my point of view, you can basically resolve the whole problem. One thing which is interesting that you might take in mind is that until Postgres 12, which is the very, very latest version, each of those CTEs, as they're called, so subqueries in a way, were optimization fences, meaning that Postgres would first execute this query in isolation. Sorry, first this one in isolation, then this one in isolation, and then this one in isolation. From Postgres 12, Postgres might choose to run them in isolation or to merge them all together, basically substituting this every time wanted appears down the line, and substituting with this missing every time it appears here, and try to optimize the query as one big query instead of separate ones. So in Postgres 12, you get both options, and you can add another keyword here as materialized in case you want to force Postgres to execute the CTE in its own separate execution context. And this is useful if you want to do more optimization. So, okay, this was a pretty tough one. The last one, the last one is the most obvious one in retrospect. You have a CPU bound process, because it turns out Spacewalk RepoSync is basically CPU bound. And it's bound to one only core, one only thread, one only process. How do you make it faster? Well, the easiest solution is to break it down and run it concurrently so that you can use more than one CPU. And this is actually what happens here. And I was pretty lucky with this patch, I have to say, because there was already a part of the code that I could isolate away in a function with a few parameters and a few returned values that was basically self-contained. And then once I broke down this part of the code in this new method, I could schedule it in multiple processes. In order to do that, I used a Python facility which is called multiprocessing pool. So what you do with a multiprocessing pool once you've created it is you can apply a function, which in this case is this method, with a set of arguments, and get it done in an asynchronous way. And pool is pretty handy because what it will do is to create the processes, the worker processes, and pickle parameters to your function, send them in binary in a binary form to the processes, and the processes will unpickle the arguments, run the function, get the return results, pickle them, send them back to the parent process, and so that you can get your result. So all of the dirty details about process creation and forking and spawning and the pickling and unpickling and transfer of all the parameters is done transparently from you, and this is pretty handy to have. The only thing that I had to take a look at was to make sure every process had its own connection, for Postgres connection. Why? Because sharing a Postgres connection across separate processes is not allowed, and it will break the client library. So each one of the processes, once it's spawned by the pool, gets its own Postgres connection, and then they can basically insert data all at the same time. Why is this important? There are a few factors. One is the fact that, as you have seen in the flame graphs, you might have not seen, but I can tell you, there are some areas of the code that are really pure Python. And those might be, they do constitute a good percentage of the overall code here. So splitting the most of the computation and working on it in parallel helps, because those pure Python code paths could be run in parallel. So getting a speed up. Second thing, I tried to use threads before using processes, but there I had the global interpreter lock from Python, really limiting my ability to scale up. And that's because, once again, we have quite a lot of Python code. It's not all native code. There's quite a lot of hot Python code in here. And third is that Postgres, until version 9.6, could really only use just one thread. So basically every Postgres connection creates a process, a Postgres client process, and that process will only use one thread. So from the same connection, Postgres is single-threaded. Of course, if you have multiple clients with multiple connections, those will go on in parallel. But from the point of view of the single client of the single connection, it's as if Postgres was only using one core. Now, here we are talking about using basically inserts. So one might think, okay, but this is mainly I/O bound, can't be CPU bound. But actually, we are doing massive inserts on a live database that has indexes, that has constraints, that has triggers. And all of those have a CPU cost every time we insert a row. So in the end, it's true, there's a lot of I/O going on, but there's also CPU stuff going on, because we have to check the constraints, we have to check the indexes, we have to update the indexes, we have to take locks, we have to run triggers. So running inserts from multiple processes and thereby using multiple Postgres client processes did provide a speed up, because the bottleneck was not really I/O, was not really the disk, but it was the CPU. Also from a Postgres perspective, not just from a Python perspective. So in the end, this was actually the change set that provided the biggest speed up overall. I think that concludes my drill down on the improvements that were proposed in these PRs. In the end, all of them combined gave something around 6-time performance increase, at least according to my tests in my scenario, in the scenarios that I've tested. What about next steps? And here I'm concluding. First of all, one can always grab a new flame graph, find out what the next bottleneck is, and fix it. This can always go on forever, and it's always true no matter what you are optimizing. So maybe at some point someone can decide that six times faster is not fast enough, we want to make it faster. So we can always start from looking at another flame graph and optimizing the important parts. The other thing that we could do, which is a little bit different, is to restructure the code in such a way processing of packages happens in parallel with downloading. Now, all of the tests that I have shown so far are with a local mirror, minimum mirror, or RMT mirror, and that means the downloading part is overall very, very fast. Actually, CPU bound, ironically. It could be, but it's a totally different scenario if we look at typical user scenarios where they have to wait hours for downloading. And in that case, it would make more sense to interleave downloading and processing so that the user doesn't have to wait for all the processing after all the downloading is finished. This is a direction that was suggested by a colleague, and I believe it's a good suggestion, and will help those cases where a mirror is not practical. So, if I had a wish, that would be the next direction I would suggest investigating for this particular tool. So thank you for listening. I hope you had fun, and you will find this useful in your next project. Bye-bye.